Hello and welcome. Today's video, we're going to be talking about one of those a lot funner applications of integrals, in all honesty, and a part where a lot of calculus students may struggle. I know whenever I was first going through calculus, this was a part, me personally, I would struggle on. And I think a big part of this came from the fact I didn't have a step-by-step method. Now, in math, it's always best to be able to try and find your own way. But sometimes just having a few guidelines really helps you to be able to find a solution. So in this video, my goal is to help you develop a pathway for evaluating volumes and working through several practice problems throughout it. So whenever we're finding a volume, I suppose what I first like to think of is the area. Or how do we actually find volumes? Well, in the case of calculus 1 and 2, we're just going to be rotating something around an axis. So in this case specifically, we might be rotating this curve f of x from around the x-axis. And whenever we're rotating this curve is going to slowly develop into a almost circular shape. In fact, it will be circular. And we're going to use this fact of rotating it around the x-axis to find a volume enclosed by this rotation. So this volume is a circle. So we're going to write this as a radius. So the radius extends from the x-axis, and we'll call it r. Well, if we want to find the entire volume, we can't add up circles. Circles don't have any volume. But what we can do is we can add little changes in x times by these circles. So we'll call this a change in x, or a circle with a width of change in x, and then a radius of r. Well, what is r, you might ask? R is just the value of f of x. So now what I want to try to do is write this as a sum. So we are going to write this, and I suppose I've kind of given this away a little, but I'm going to come back to this. Well, we know that we're adding up a sum. Let's say from I is equal to 1 to n. We're summing up pi, because this is a circle, times by f of x squared, which is the radius of said circle. So we'll call this f of x of I squared, times this by a very small width change in x. Well, this alone is just an approximate area. So what we're going to do here is we're going to take the limit as n approaches infinity. I don't think it's going to let me write. There we go. And what this becomes is the definite integral from a to b, or let's say pi times the integral, from a to b of f of x of I, or really just f of x, squared dx. And this function right here, or whatever this value is going to be the volume of the function rotated around the x-axis. However, what's important is that you really need to keep in mind this r, and we're going to do some problems where this r might change later on. So what I've really said here is for like the steps is divide it into small pieces. We want to take small little slices of the area. Then we want to write it as a Riemann sum. Then take the limit as n approaches infinity. And this is going to make the area exact or make it into a definite integral. And then evaluate. So we want to find the volumes of the following rotated around the x-axis. from 0 to 2 for this first one. Okay, so I'm going to start by sketching out a graph. And we know that this is going to probably look something like this. Yeah, that looks about right. Because we're going from x... Yeah, there we go. And we're rotating this curve y around this x-axis. So what we're going to get is we're going to get kind of a shape kind of like this. And I'm sorry I'm not the best at drawing 3D shapes. So, in order to evaluate this, we're going to divide this shape up into very small radiuses, which have the radius of x plus 1. So, and then we're going to multiply this by a little change in x, and then sum it all together. So what this is really going to look like is the integral from 0 to 2 of, apparently I wrote 2 twice, but y squared, which in this case is x plus 1, squared dx. And remember to multiply it by pi, because this is a circle. This here, or this inside function, is the radius of the circle squared. We just took out the pi. So, now what we're going to do is we're going to expand this out so we get pi times by the integral of x squared plus 4x plus 1. Or, sorry, not 4x, 2x plus 1 dx, evaluated from 0 to 2. Now, integrating this, we get x cubed divided by 3 plus x squared plus x, evaluated from 0 to 2, times by pi. Well, plugging these values into the function, we get 8/3 plus 4 plus 6 minus 0 times by pi. Well, this 4 plus 6, that evaluates to 10. And then plus 8/3, that's going to be 2, and then a remainder of 2/3, so 12.66. 66. And then I don't have a unit for volume, but that does kind of sound right, doesn't it? Forgot to multiply it by pi. So 12.66 pi. And that would be the volume for the shape. So for this next one, curve, what we have to do is we're going to draw out a small little graph, although this one I'm going to make a bit smaller. And this is going to be going from 1 to 5. And it's going to look something like this. So we're going to rotate this curve around the x-axis. Again, we're going to have a radius, or we're going to draw in these little circles here. It's going to have a radius of whatever the square root of x minus 1 is, and then a change in width of change in x. So we're going to just say that this is going to become the integral of the square root of x minus 1 times by pi from 1 to 5 dx. Well, integrating this function, I'm going to say that u is equal to x minus 1. Oh wait, sorry, I forgot to square this, so this actually doesn't need u sub. So we get pi times by the integral of x minus 1 from 1 to 5 dx. So we get x squared divided by 2 minus 1 times by pi, evaluated at 1 to 5. minus 1x, sorry. There we go. Okay, now what we have to do is we just have to plug in values. So we get 25 divided by 2 minus 5 minus, and I'll put this in parentheses, 1/2 plus, or sorry, minus 1. And then simplifying, well, 25 minus 1/2, or in this case, yeah, minus 1/2. Apparently I forgot to put parentheses around things, so give me one moment. Parenthesis there, minus there, there we go. So we get minus 1/2, which is going to make this 24 divided by 2, which is 12. And then we get negative 5 minus 1, which is going to be negative 6. So we get 6 pi for our answer. Give me one more. Now we want to find a method for finding the area bound by two curves. And this is really called the washer method. So what we're really going to do with the washer method is we're going to recognize that this could be seen as an area of a bigger circle. So we're going to still rotate this about the x-axis. And this could be seen as the area of a bigger circle minus the area of a smaller circle. So whichever function is greater than the other, in this case y is equal to x is greater than y is equal to x squared from 0 to 1, we are going to say that that area is going to be minus the smaller area. So what's this going to look like? Well, this is going to look like the integral from pi from a to b, and let's just call this curve in general the bigger curve. We'll do this in green. F of x squared dx plus, and I'll do this part in pi, plus the integral, pi times the integral, rather, from a to b of the lesser function, in this case orange, so we'll call this g of x squared dx. So we can now condense these integrals by factoring out a pi, so we get the integral from pi of a to b of the outside function, which I'm still going to do in green, hopefully, f of x squared plus g of x squared dx. And I really wanted to say minus for all of this. Messed up a little there, but that's okay. So really we're taking the bigger area and then subtracting the lesser area from it. Alright, now applying this formula that we've kind of found here to our function, or our graph here, we want to really find the area from 0 to 1. And we're revolving it around the x-axis, so we've already drawn that in. It's going to kind of look like a very strange shape there, but we're going to get f of x. And what we're really revolving around the x-axis is this area right here, and we're turning this area into the volume. That's what we're truly rotating around the x-axis. So we get f of x squared, which is just going to be x squared, minus g of x squared, which is going to be x to the power of 4 dx. Evaluating this now, 1 to 0, of x cubed divided by 3 minus x to the 5th divided by 5. Don't want that there anymore. And then evaluate it from 0 to 1. Well, at 0, that's just going to be 0, so we can take the simple step here and just evaluate it at 1. You get 1/3 minus 1/5. Finding a common fraction here, we would get 5/15 minus 3/15, so 2/15. So we get pi times by 2/15, which is going to be 2 pi/15 for our answer of the volume. Not very high, not very much volume there. Okay. So now we want to look at these next functions and then revolve them around the y-axis. So sometimes we can revolve functions around other axes, like the y-axis. And in both of these problems, we will be doing that, where we're revolving a function around the y-axis instead of the x-axis. So sketching out a small bit of a graph here, let's see what this is going to look like. So we have our functions. We got y is equal to x squared, so that's going to look something like this. And then we have y is equal to 2x. So because we're revolving this around the x-axis, give me one moment to think here. What I really want to do is get these functions in terms of x is equal to y. So we are going to say that x is equal to the square root of y, and x is equal to 1/2 of y. Alright, and now that we have this in terms of y, we can now use these to find our radius. So our radius here, or our inside radius, or lesser radius, is just going to be 1/2 y. However, our greater radius, larger radius, is going to be the square root of y. So now what we're going to do is we're going to integrate this from where these two curves are equal. Well, where is 2x and x squared equal to each other? Well, at 0 and also 2. So we're going to be integrating this from 0, and let's real quickly find that in the y term, which is going to be 4. So if we set these curves equal to each other, we'd get 1/2 of y is equal to the square root of y. Here, let me actually real quickly solve this. So we'd get 1/2 y is equal to the square root of y. Alright, so then we'll square both sides, let's square both sides. So we get y is equal to 1/4 y squared. Move that over to the other side, so we get, we get 1/4 y squared minus y. Factoring out 1/4 y, we would get y minus 4. And we can clearly see that this is going to be from 0 to 4. Okay. Or now we are going to be taking our outside function and squaring it, which in this case is the square root of y squared minus 1/2 y squared times by our dx, or dy in this case, because we're taking the integral with respect to y. Well, the square and the square root will cancel, and then this will distribute, so we're going to get really the integral from 0 to 4 of y minus 1/4 of y squared dy. Integrating this now, we will get y squared divided by 2 minus 1/12 of y cubed evaluated from 0 to 4. Well, the cool thing about this is because there's no constants or anything at 0, it's just 0. So we just have to evaluate this at 4. So 4 squared is 16. 16 divided by 2 is 8. 8 minus, well, 4 cubed is 64. Divided by 12, I don't think that cleanly goes into that. So we get an answer of 8 minus 5 1/3. After I did the math. Alright, so 5 1/3, so that would be 2/3. 2 and then 2/3. However, we did forget one important detail. We forgot to multiply by pi. So this is going to be times by pi. And that would give us our final answer. For these next two equations, they're already given us in the form x is equal to y. So all we have to do here is solve for where they're equal to each other and then integrate. So, well, first I suppose I do want a graph. So, let's see. We have the function 2 minus y squared. So this is going to start at 2. And this is going to be a parabola that opens to the left. Y to the power of 4 is going to be a parabola that opens to the right. Or a parabola shape. This area right here is what we're rotating around the x-axis, or the y-axis, and it's going to have a radius. So it's going to always have a radius, or the outside radius, or the greater radius of this 2 minus y squared. It's going to have the inside radius of y to the 4th. So now we have to do is we just have to expand this out and then integrate. So we get the integral, or first let's solve for this is equal to each other. So we get 2 minus y squared is equal to y to the 4th. All right, let's solve for y to the 4th here. So we get y to the 4th plus y squared plus 2. How do I want to solve this? Maybe I can say u is equal to y squared. So we would get u squared plus u plus 2. However, I don't think this has any viable solutions. Give me one moment. Okay, so it's minus 2, sorry. That's what I was messing up. So now what we can do is we can factor this. So we get u minus 2 times by u plus 1. Well, now we just have to sub in the y squared. Whenever we're subbing into here, this is never equal to 0. So we're just going to worry about y squared minus 2 and setting that equal to 0. So this is going to happen when y squared is at 2, so y must be equal to plus or minus the square root of 2. This is going to be a not-so-fun integral. Okay. And here I thought I was creating carefully constructed problems. No, I'm kidding. Okay, so we're doing the integral, or pi times the integral from negative square root of 2 to the square root of 2. Alright. Ooh, actually, this might actually turn out a small bit nicer than what I thought it did. So, I accidentally said that this should be minus, it should be a plus. This should be the minus. Because this is the minus, we only have to worry about y squared minus 1. This, however, does work out prettily to be y is equal to plus or minus 1. So instead of having to deal with this irrational number, We just have to do with -1 and 1. And as always, remember, it's okay to make mistakes. I show all of mine, as I hope it will help you with your journey with math. So we get 2 minus y squared, and then square it. Minus y to the 4th squared dy. That is not going to be a very fun integral here. So we get we get the first squared minus twice the product, which will be 4y squared, plus y to the 4th minus y to the 8th dy. Alright, now we get pi, and I'm actually going to say something here. Yes, this is an even function, because if I plug in a -y, it should theoretically be the same. So I am going to just do a quick little trick and call this 2 pi times by the integral from 0 to 1 of 4 minus 4y squared plus y to the 4th minus y to the 8th dy. Now, doing the calculus, you get 4x minus 4/3 y cubed plus y to the 5th divided by 5 minus y to the 9th divided by 9. Alright, evaluated from 1 to 0. So we get 2 pi times by 4 minus 4/3 plus y over 1/5 minus 1/7. I feel like this is like a something special in math, but I'm pretty sure it's not. 2 pi. Well, I'm not going to really evaluate this. If you want, you can, but I'm not going to, as that's a scary number. No, not really. It's perfectly fine to evaluate. You just have to get common denominators here, but because the video is running a bit longer, I don't want to. So revolving around other axes. So I always recommend, if you're revolving anything but the x or y axes, draw a diagram. It will save you from making so many mistakes in my experience. So you want to draw a diagram, write an expression, and then find the volume. So find the volume of the shape enclosed by rotating the curve x squared and y squared around y is equal to 1. From 0 to x is equal to 1. Okay, so to start out, draw the curve, or draw the graph. We know y is equal to x squared is going to look something like this. We know x is equal to y squared. Well, I have a little trick for you. We're going to call this y is equal to the square root of x. So it should look the exact same, just reflected over the line y is equal to x. They should intersect at the point 1, which is kind of interesting. But we're integrating this about this line 1, 1. So y is equal to 1. So what we have to do is we have to find our inner radius and our outer radius with respect to this line. So, in this case, our inside radius is going to be the square root of x. Our outside radius, or our greater radius, is going to be x squared. So what our integral is going to look like is it's going to be the integral from 0 to 1 times pi times that, of course. Alright, and then it's going to be this x squared minus the square root of x squared dx. So now what we have to do here is we're going to just evaluate this integral as normal. We get x to the fourth here minus x dx. And then now evaluating the integral, we get x to the fifth divided by 5 minus x squared divided by 2. Evaluated from 0 to 1. Well, at 0, this function is just going to be 0. So we get pi times by 1/5 minus 1/2. Well, getting a common denominator, we get 2/5 minus 1/2, which is going to give an answer of pi times by -3/5. So -3/5 pi. Now give me one moment to fact check something. I believe this area should just be, or this volume should be 3 pi divided by 5. The reason that this negative showed up is because this curve is really just beneath the y, or the axis of rotation. So in this case, I do believe, because the area is underneath y is equal to 1, the volume is going to be, it's going to mathematically be like -3 pi over 5, but because that doesn't make sense in the real world, the true answer is 3 pi fifths, just because of definition of volume. I hope you all have enjoyed this video, and if you did find it informative, please make sure to like and subscribe. Goodbye.